Welcome everyone, and thank you for joining me today. I'm excited to present to you the complete guide to plumbing systems. We'll be exploring design, calculation, and standards, both local and international. Over the next few slides, we'll cover key concepts, best practices, and important standards that will help you understand and implement effective plumbing solutions. Let's get started. Let's take a look at the cold and hot water supply network. Here, we're focusing on some key points that are essential for designing an efficient system. First, fixture units. These are a way to estimate the water demand based on the types and number of fixtures connected. Understanding demand helps us size the pipes and equipment properly. Next, pump head is critical because it determines the energy needed to move water through the system. It's directly related to the height and resistance the pump must overcome. Velocity limits are also important because maintaining appropriate flow velocities helps prevent issues like noise, erosion, or pipe damage. Now there's a handy formula here. Equals 10.67 times the length L times the flow rate Q raised to the 1.852 power, divided by the pipe's coefficient C raised to the same power, and multiplied by the pipe diameter D raised to the 4.8704 power. This formula helps us calculate head loss due to friction in the pipes, which is vital for system design. Finally, on the 3D exploded view, you can see the key components: pumps, tanks, risers, and the distribution manifold, all interconnected. Visualizing these elements helps us understand how they work together to deliver reliable water supply. Ultimately, these points tie back to our overall goal: designing a system that's efficient, reliable, and capable of meeting demand smoothly. Let's talk about hot water and recirculation. The key points here are the domestic hot water, or DHW load, which is essentially the demand for hot water in the system. We also have the storage tank, which holds hot water for later use, and the recirculation line, which helps maintain hot water availability throughout the system. Now, when we look at the formula Q sub R equals U times A times delta T divided by C sub P times delta T allowed, we're quantifying the heat transfer rate needed for recirculation. This helps us understand how much energy is required to keep hot water circulating efficiently. If we break down the components, you'll see the exploded view includes the heater coil, which heats the water, the pump loop that circulates it, and safety devices like the pressure relief valve, or PRV, and the temperature mixing valve, or TMV. These elements work together to ensure safe, efficient, and reliable hot water delivery across the system. Connecting this to the overall theme, optimizing hot water recirculation not only improves comfort, but also enhances energy efficiency and safety in building systems. Let's take a closer look at the fixture connection layout. Here, you'll see how we consider fixture units, which are essential for determining the proper pipe sizing based on the expected demand. It's important to get the branch sizing right so that each fixture receives adequate flow without causing pressure issues. Speaking of pressure, maintaining a balanced pressure throughout the system is key to ensuring all fixtures work efficiently and consistently. Now, on this exploded view, you can see the individual fixtures, like the sink, water closet, and shower. Notice the flow arrows indicating how water moves from the main supply through each branch. And don't forget the trap seal. It's crucial for preventing odors from entering the space. Understanding this layout helps us design a plumbing system that's both reliable and efficient, tying back to our overall goal of creating a safe and functional building. Now, let's take a closer look at sanitary drainage and vent systems. One key concept here is the drainage fixture unit, or DFU, which helps us estimate the flow capacity needed for different fixtures. Proper slope is also crucial. It ensures that waste flows smoothly without backups or stagnation. Venting plays an essential role as well. It prevents siphoning of trap seals and allows air to enter the system for proper drainage. When calculating flow rates, we use the Manning formula. Q equals 1 over N times the cross-sectional area A, times the radius R raised to the 2/3 power, times the slope S raised to the 1/2 power. This helps us determine the capacity of pipes accurately. In the exploded view, you can see the different components: soil lines, waste lines, vent lines, and how they connect and slope. Understanding how these elements work together is vital for designing an efficient and code-compliant sanitary drainage system. Let's take a closer look at stormwater drainage, which is a crucial part of our overall drainage system. One of the key methods we use to estimate flow is the rational method. The formula for this is Q equals 0.00278 multiplied by C, I, and A here. Q represents the peak runoff in cubic meters per second. C is the runoff coefficient, I is the rainfall intensity, and A is the catchment area. This helps us determine how much water we need to manage during a storm event. Now, shifting focus to roof drain sizing, it's essential that we size these correctly to handle the expected flow. The process typically involves an exploded view, starting with the roof, which collects the water, then directing it through a downpipe. From there, the water flows into a sump, which acts as a collection point, and finally, it's channeled into a soakaway where the water safely infiltrates into the ground. Connecting all these points, proper stormwater drainage design ensures that water is efficiently collected, directed, and absorbed, preventing flooding and protecting the building and surrounding environment. It's a vital part of our overall approach to sustainable and safe infrastructure. Let's talk about firewater and cross-connection prevention. One of the most important concepts here is ensuring proper separation to avoid contamination. This means keeping the firewater system isolated from other water systems to prevent any backflow issues. A backflow preventer is a critical component in this setup. It acts like a one-way valve that stops contaminated water from flowing back into the clean water supply. Additionally, a break tank is often used to provide a physical separation and help regulate pressure, ensuring that water flows correctly and safely. Now, if we look at the exploded view of the fire pump room, you'll notice the suction and discharge headers. These are key to understanding how water moves through the system. The suction header draws water into the pump, while the discharge header pushes it out to where it's needed, such as sprinklers or hydrants. Everything needs to be carefully designed and maintained to prevent cross-connection and ensure reliable fire protection. Connecting these points to our overall theme, it's all about safeguarding the water supply and maintaining system integrity. Proper separation, backflow prevention, and careful system design are essential for a safe and effective fire protection system. Let's take a closer look at equipment and valves. First, we'll discuss the different types of valves commonly used in our systems. These include gate valves, globe valves, check valves, pressure relief valves, and pump internal parts. Each type serves a specific purpose and has unique characteristics. Understanding the control strategy is also essential, as it determines how these valves operate within the system to maintain safety, efficiency, and reliability. We need to choose the right valve type based on the flow control requirements and the process conditions. Materials are another critical aspect. The materials used for valves and equipment must withstand the operating environment, including temperature, pressure, and potential corrosive elements. Proper material selection ensures durability and long-term performance. If you look at the exploded view, you'll see how each component fits together, like the gate and globe valves, which control flow, or check valves that prevent backflow. The pressure relief valve, or PRV, is vital for safety, releasing excess pressure to protect the system. And inside pumps, the internal parts are designed to optimize flow and efficiency. All these elements tie back to our overall goal of ensuring a safe, efficient, and reliable operation. Understanding the different equipment types and their materials helps us make informed choices and maintain system integrity. Let's take a closer look at this design example. Here, we're imagining a 6-floor dormitory that accommodates around 180 residents. To better understand how the water system works within this building, we've used an exploded view. This means we've broken down the layered water system into its different components, so you can see how each part interacts. We've included features like slopes and flow pathways to illustrate how water moves efficiently throughout the structure. And to make everything clearer, we've added a transparent shell around the model, so you can see the internal workings without obstruction. This kind of detailed visualization is really useful because it highlights the importance of thoughtful design in managing resources like water. It also connects to the broader theme of creating sustainable, efficient, and user-friendly architectural solutions. By examining this example, we can better appreciate how layered systems and transparent visualization techniques help us optimize building performance and user experience. Let's take a closer look at standards and testing. When it comes to plumbing and piping systems, there are several key standards to keep in mind, such as IPC, UPC, and SBC. These codes help ensure that installations meet safety and quality benchmarks. Additionally, references from organizations like NWC, AWWA, and NFPA are crucial. They provide guidelines for water quality, fire protection, and system integrity. Now, when we talk about testing, imagine an exploded view of the components involved. You have the pump, the pressure gauge, and a pipe section under test. Visualizing this setup helps us understand how we verify system performance and safety. Testing is essential to confirm that everything functions correctly under pressure before the system is put into service. Connecting this to the bigger picture, adhering to these standards and thorough testing ensures reliable, safe, and compliant plumbing systems, which is ultimately what we aim for in every project. Now, let's talk about QA, QC, and handover, which are crucial steps to ensure everything is up to standard before we move on. First, pressure testing is essential. It verifies the integrity of the pipe segment under the maximum expected pressure, helping us catch any potential leaks or weaknesses early on. Flushing comes next, where we clean out the pipeline to remove debris or any residual materials that could affect performance. Disinfection is equally important, especially in potable water systems, to ensure the water remains safe and free from harmful bacteria. Inspection reports are the final checkpoint. These documents confirm that all tests and procedures have been completed successfully and meet our quality standards. If you look at the 3D exploded view, you can see key components like the pipe segment, pressure gauge, technician, report clipboard, and chlorination skid. All of these elements work together during the QA/QC process to ensure a reliable, safe handover. This phase ties back to our overall goal of delivering a robust and safe infrastructure, emphasizing the importance of thorough testing and documentation before the system is handed over for operational use. All right, let's take a moment to review the summary and legend slide. As you can see, we've included icons representing each network type: cold, hot, sanitary, storm, and fire. These icons help us quickly identify the different systems throughout the model. In the 3D exploded view, the model is shown in a more detailed way, with each system color-coded for clarity. This makes it easier to understand how each network functions and interacts within the overall design. The legend box is a key part of this slide. It explains what each color and symbol represents, so there's no confusion about the different systems at a glance. Overall, this slide encapsulates the entire network setup and serves as a quick reference guide, tying together the detailed information we've discussed earlier. It highlights the importance of clear visualization and proper labeling in complex systems like this, which is essential for effective planning, construction, and maintenance. So, in essence, this summary helps reinforce our understanding and ensures everyone is on the same page about what each network type is and how they coexist within the project.